All right, so Fubini's theorem. This is a big result in multiple integrals. Um, right, the subtitle here is please don't make me do multivariable Riemann sums. If you saw my previous video on multivariable Riemann sums, you probably left that video going, "Oh dear, really? This is what a double integral is, right?" Um, and yes, that's what a double integral is defined to be, but it's not. It's not the end of the story, right? It much like in Calc 1, you learn Riemann sums, but then quickly you get the fundamental theorem of calculus, and you learn instead to evaluate integrals using antiderivatives. Same thing here, right? So this is what Fubini's theorem is it lets you evaluate double integrals using antiderivatives, right? Much like you do in Calc 1. So here, what do we have for this theorem, right? For this wonderful theorem, Fubini's theorem. We have, let's read it and illustrate it as we read it, right? So we have R is some region in the plane, right? So we have our good old XY plane, and I'm drawing it, sort of flattened down because I want my z-axis as well, right? But R, capital R itself, just exists in the XY plane, right? And it's bounded by x equals a, right? So some coordinate on the x-axis a, some coordinate b, right? And then it has an upper boundary that's given by some function, and this function is going to be the graph of y equals f of x, right? And then some other function is the lower bound, y equals g of x, right? So this is our region R, is this little boundary in the plane, right? So R is a domain in the xy plane, and it's a domain for this continuous surface f, right? So then now we plot, in R, plot this surface f, right? So you have, it might have different heights at different points, right? But maybe it has bubbles up and has a little rise and fall. So there we go. So there's the graph of this surface z equals f of xy, and it's continuous above R. Maybe it isn't continuous elsewhere, maybe it's undefined elsewhere. We don't really care, but at least on R it's continuous. Okay, so then the double integral of f over R, which is the volume, right? This is the volume of this region. So V is this, this volume of this solid in here, right? That's bounded below by the xy plane and above by f. This volume, right, which is the double integral, is given by what? It's given by an iterated pair of two single integrals, right? So this, notice here, this is an ordinary single integral, right? You're going to evaluate that. What is this saying to do? It's saying you're going to take an antiderivative, just like you would back in Calc 1. Take an antiderivative of f, but here it's kind of like a partial antiderivative, right? You're going to use y as the variable, right? And just treat x as constant. And so what's the mindset there? What you're doing is you're imagining that you fix some particular x in this interval, and at that x coordinate, you're coming over here and you're calculating an area, right? You have this kind of 2D slice of that 3D solid, and that's what that integral is going to represent. This should look very similar if you've seen volume by cross sections. It's very similar to what you do when you do cross sections. It's just a little more general, right? So this essentially would be the area of the cross section, right, of our solid at x, right? So this should give you some formula in terms of x once you calculate this, right? Once you do the antiderivative, right, and plug in the bounds, right? You plug in y equals fx, then you subtract, right? Then plug in y equals g of x, right? And when you do all that, after you complete all of that, now here you have this a of x, right? You have some formula in terms of x that gives you basically the area of the cross-section at x, right? And then you hand that off to this outer integral, right? See, so now this outer integral just looks like kind of a normal Calc 1 style integral. It's just that this a of x happens to represent the area of a cross-section of this 3D solid, right? And then you calculate that, and what that's doing is that's taking all of these slices from, you know, the very first one to, you know, the second slice, third slice, fourth slice. I mean, there's not really a first, second, or third, right? But you imagine putting together these cross-sections all the way across the figure until you get to that cross-section at x equals b, and it adds up, it integrates, right, the areas of all of those cross-sections. And when you put that all together, that gives you the volume. And that's the double integral, right? So this is a you know, explanation of how Fubini's theorem works. Let's see it in an example, right? So let's do a little example, right? Let's use Fubini's theorem to find the area of the parallelogram with vertices at 0, 0, right, 1, 3, 3, 5, and 2, 2. Right, so let's use Fubini's theorem to find this area. So first of all, you might look and say, wait, Fubini's theorem calculates volumes, not area. What is going on, right? Well, so this is the first observation, is, I want to note here, right? So note that if you want the area of the region R, what could you do? You could think of it as the double integral of the function 1 dA, right? So think of it almost as a constant surface. Right, with height 1. So you could think of it as, you know, think of it as if you had a box of height 1, right, and you do length times width times height on that box, well, the height is just 1, so you just get length times width, which is just area of the base, right? Which is a little weird because we're mincing units. We're kind of arbitrarily, you know, going between meters cubed and meters squared, but the number comes out correctly. Or you can think of it as a density function, right? You can think of it as density 1. And then you could say, okay, if I have density 1, then area and mass are the same, right? So you don't have to think of it as a height at all. If you want, you can just think of it as a density, and then that's, you know, maybe keeps the units a little more sound, right? So let's so that's a note of how we can find an area using Fubini's theorem. So let's do this now, right? Let's look at this parallelogram. And let's see here. So I have my vertices. So I have 0, 0, right? I have 1. Oop. I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right, and so I have 0, 0 is one of the points. I have 1, 1, 3 is one of the points. Right. I have 2, 2 is one of the points, and I have 3, 5 is one of the points. So here's my little parallelogram. Okay, and then I want to use Fubini's theorem here, and you might look at this figure and say, what are you talking about, right? This doesn't look like an R at all in terms of the R's we talked about here, which are bounded by constants with respect to x, and then functions with respect to y, right? This is kind of kooky. Well, yeah, you can't do it as stated, but you can do it in a couple applications of Fubini's. You could do it once here, right? So we'll do it from x equals 0 to x equals 1. Then we'll do it again from x equals 1 to x equals 2. And then we'll do it again, right, from x equals 2 to x equals 3. So we'll set up this double integral as 3 separate integrals. So call this region 1, region 2, and region 3. And together, our region R, is the union of these 3 regions. Right? And these regions are just bounded by different functions, right? So depending on which region I'm on, I'll use different functions, right? So let's get the equations for these functions. So the easiest is this bottom one is just y equals x, right? The one next to it on this boundary, that one's not too bad, right? That one's y equals 3x, right? Slope 3, intercept 0. And then I need these other two, right? So here, the easiest way to get this function is just notice that it's slope 1, right? So if you just trace it back to the y-axis, it would have a y-intercept of 2, right? So you'd have here, you're going to have y equals x plus 2 is that top one, right? And then the hardest one to get is on the right-hand side, but I mean, it's not exactly difficult, right? It's slope 3, and then you just need to say, okay, it's y equals, it's slope 3, and then we just need to know what b is. But here, it's just a little hard to see b geometrically. So here I would just plug in a point, right? So we have, it passes through 2, 2. So if you put 2 for y and 2 for x, then we have 2 equals 6 plus something, so negative 4. There we go. Right, so 3x minus 4, that's that last y. And you could check it by just plugging those points in, right? Say, for example, 3 in for x, 3 times 3 is 9, minus 4 is 5. So there we go, there's 3 comma 5. So there we have the functions that form the boundary of our parallelogram. So then, what could you do? You could say, now let's do the double integral, right? Because what is the area? The area is the double integral of 1 across this region R. And here, like we said, we're going to actually set this up as a sum of 3 double integrals, right? Because this region R is being, you can't really set it up all at once, right? There we go. And now we can set it up as per Fubini's theorem, right? So the first integral goes from 0 to 1, right? And the bounds are what? The bounds, it's y equals x on the bottom, and it's y equals 3x on top for the region R1, right? Then I have my next region, x equals 1 to 2. And there, the bottom bound is still x, but the top bound is now x plus 2, right? It's a different bound up top. Lastly, we have x equals 2 to 3. And there, my bottom bound now changes, right? I have this 3x minus 4 for the bottom bound, and I have x plus 2 for the top bound. There we go. Right? So there's our setup for all our integrals. Now I can integrate, right? So fortunately here the antiderivative is squeaky clean, right? It's just y in all 3 cases, because the antiderivative of 1 is y. Oop, plus, not equals. There we go. Then I can plug in these functions. Right, this is just like Fundamental Theorem of Calculus back in Calc I, right? You plug in the top bound, you subtract, you plug in the bottom bound after having taken the antiderivative. Parentheses, of course, are important if you're subtracting a bottom bound with two terms, right? Okay, and so now clean these up a little bit, and then we're going to do an antiderivative with respect to x once we get them cleaned up. So here I'm just combining like terms. Right, note the double negative on the 4. This actually becomes plus 6. Easy place to make a simple mistake. Right? Now, antiderivatives, right? So this is going to be x squared from 0 to 1. This is going to be 2x from 1 to 2. This is going to be negative x squared plus 6x from 2 to 3. Now, plug in and subtract, right? Plug in and subtract, right? Plug in and subtract. Right, so we plug in, let's see, we plug in 3. Oops. Yeah. We plugged in 3, then plug in 2. Oh no, that was good. That was right. And then subtract. Yeah. Okay. And then arithmetic, right? I have 1, I have 2, I have 9, I have 8, right? And I get 4. So there we go. So after all that, we get 4 as the area of that little parallelogram, right? Okay, wonderful, right? So this was, you could think of it as the parallelogram's area, once again, or you could think of it as the parallelogram's mass if the density was constant function 1. Or you could think of it as, kind of literally what we did. You could think of it as the volume of, you have that parallelogram, and then you build a constant surface of height 1 off of it. Right, and then you have this parallelogram prism, right, and it's the volume of that, is volume 4. However you want to interpret it. They're all valid interpretations. Note here, this is area of a parallelogram. We have other ways to solve this problem, right? Let's check it. We're testing out a new tool. Let's check it. In particular, let's confirm with using a vector geometry. Right? Remember one of our really nice properties about cross product. If you want to interpret what does the magnitude of a cross product mean? The magnitude of a cross product means the area of the parallelogram, of the corresponding parallelogram, right? So in this case, what is V and what is W? Well, let's go up here and let's get those vectors, right? So I have, let's see, V, if you say vector V, that's just going to be 2, 2, right? And then what is W? W is 1, 3. Right? Now here it's 2D cross product, so you don't really need like vector magnitude. You can just think of it as a number and do the absolute value. So here what do we get? We get an absolute value of 2 times 3 is 6, minus 1 times 2 is 2, and we get 4. Which of course is immensely easier, right? This is very typical. Usually if there's a problem that you could solve with either geometry or calculus, usually geometry is so much easier. But the calculus is way more general, right? If you play with the figure a little bit, you change it a little bit, and you make, say, one boundary parabolic instead of linear, right? Well, now you can't do the cross product formula anymore, but you can still do this double integral Fubini's theorem approach. So There we go. There's our theorem. There's an example of using it. And I will talk to you next time.